Hi everyone, this is video number 5 of our P3 chapter 10 lectures. Currently on the screen is page 11 of your P3 chapter 10 notes. In this video, we'll study about Argand diagram. The Argand diagram is a very important thing to learn in this chapter. And in the later parts of this chapter, it will encounter will encounter more and more use of Argand diagram. The first part is an Argand diagram. Okay, so an Argand diagram is actually just our usual x and y axis. The usual Cartesian plane formed by using the x-axis and the y-axis. And now we call it an Argand diagram when we rename the x-axis as the real axis. The x-axis is renamed as the real axis, while the y-axis is renamed as the imaginary axis. And then we get an Argand diagram. And so in short, Argand diagram is just our usual xy plane, right? A plane that is formed by using the x-axis and the y-axis. Just that now we do not call the x-axis as the x-axis anymore. Right? We rename x-axis as a real axis and the y-axis as the imaginary axis. And the way to label the axis will be RE bracket Z and IM bracket Z respectively. And so there are also certain books that label their real axis as REZ without bracket around Z. This is also acceptable, while the y-axis is IMZ. Okay. So what is REZ and IMZ? These are notations that you've seen before earlier in this chapter. Recall that if Z is 3 plus 4i, then the real part of Z is 3 and the imaginary part of Z is 4. Okay, so this actually allows us to plot the point representing the complex number Z on the Argand diagram. Now, if we want to plot 3 plus 4i on the Argand diagram, we know that the real part is 3, imaginary part is 4. In other words, the x coordinate would be 3, and the y coordinate would be 4. So you can actually plot this point, and that point that I have just plotted on my Argand diagram will be the point representation of the complex number Z. Let me just state it here. This would be the point representation of the complex number 3 plus 4i. Okay, now let's move to point number 2 of the notes. In this chapter, we have learned that a complex number in general can be written in the form x plus yi, where x and y are real number. And so here it is telling us that any complex number z that is written in the form x plus yi, it can be represented by the point with coordinates x, y on the Argand diagram. And so for example, we can represent the numbers z1 equal to 2 plus 3i. So the point representation will be the coordinate 2, 3. Coordinate 2, 3, which they have plotted for you as the point A there in the diagram. This is the point 2, 3. So this point A would be the point representation of the complex number 2 plus 3i. And point B with coordinates 5 minus 3. This is the point representation of the complex number Z2. Because Z2 is 5 minus 3i. So the way to represent a complex number as a point on the Argand diagram is very easy. The real part of the number becomes the x coordinate, while the imaginary part of the complex number becomes the y coordinate. Right, so in this printed diagram, it shows you the point representation of the complex number Z1 and Z2 respectively as points A and B. Now, point number 3 is to tell us a different way to diagrammatically represent a complex number on the Argand diagram. Point number 3 introduces us to vector representation. Okay, so it is using the same example, Z1 and Z2, the 2 plus 3i and 5 minus 3i is the same two complex number. Earlier in point number 2, they have already plotted the point representation of those two complex numbers on the Argand diagram. Now in point number 3, they say, using the same points A and B just now, if you connect a vector from the origin to the point A and also from the origin to the point B, the vectors OA and OB are respectively the vector representation. And so OA and OB are vector representation of the complex numbers Z1 and Z2 respectively. Right, so understanding of this vector representation will be very useful, especially when we want to visualize what happens when we add or subtract complex numbers, okay, which we'll cover on page 12. Okay, now let's move to page number 12. Oh, and by the way, the vector representation of complex number, which we'll encounter in this chapter, they are all only two-dimensional vectors. Because the Argand diagram is just a two-dimensional plane. It's just a two-dimensional surface. So any vectors on the Argand diagram will be two-dimensional vectors. So for example, the vector OA that represents the complex number 2 plus 3i, it is the vector 2i plus 3j. This is the vector 2i plus 3j, which we usually prefer to write in a vertical bracket form. So this is only a two-dimensional vector. The vector OB, which represents Z2, 5 minus 3i, it is 5i minus 3j. Notice that this I with a curly line and the I without a curly line have different meanings. The I without a curly line is the imaginary unit, while this I with a curly line is a standard unit vector pointed to the right. Okay, yeah. So the vector representation of complex number are all two-dimensional vectors in our syllabus. Okay. Now let's move to page number 12. A graphical representation of addition and subtraction in an Argand diagram. So here it is telling us that because we have already learned how to represent complex numbers using vectors, the addition and subtraction of vectors, it can be visualized on an Argand diagram using our knowledge on vectors. Okay, so let's recall from the vectors chapter. If your vector u is pointed this way, and your vector v, for example, is pointed vertically downwards. And then when you add up u and v, it is just a vector u. The end of the vector u becomes the starting point of the vector v, and then you just draw vector v here, and maintaining the length and direction, of course. And recall that vectors are free in the sense that they can be moved around as long as the length and the direction remains the same. Right, so the starting point of u and the ending point of v here, if we connect them using a straight line, this green colored vector, it will be the resultant vector of u plus v. And this is how we visualize addition of vectors. So here in Argand diagram, it works the same way. Now let's look at point number 2. Okay, let Z1 and Z2 be two complex numbers represented by OP1 and OP2 respectively on the Argand diagram. And so here let's suppose that the point P1 with coordinate x1, y1 is here, point P2 with coordinate x2, y2 is here. Right, then P1 and P2, they are the point representations of the complex numbers Z1 and Z2 respectively. And vectors OP1 and vector OP2, those are the vector representation of the two complex numbers Z1 and Z2. Okay. Now, to add up Z1 with Z2, the vector representation of Z1 plus Z2 can be obtained by, let me draw a new diagram here. So you know that your OP1 points this way. OP1 points this way. So the OP2 that I'm coloring in pink here, you can actually connect it, you can actually move it such that the starting point of OP2 uh, overlaps with P1. So I can actually move my vector OP2 and I put it here, and maintaining the length and direction. Okay. So my red color vector is the same as my vector OP2 because it has the same direction and same length as the vector OP2, right? So the blue vector is OP1, red vector is OP2. So if I connect from the very beginning starting point and the ending point there using a straight line, my green color vector, it will be the resultant vector that represents vector OP1 plus vector OP2. OP1 plus OP2. Hey, but we know OP1 is actually the vector that represents a complex number Z1, and OP2 is the vector that represents a complex number Z2. And so this green colored vector, it is not only the resultant vector of OP1 plus OP2, it is also the vector representation of the complex number Z1 plus Z2. I repeat, the green color vector, it is the vector representation of the complex number Z1 plus Z2. And if you read this coordinate at the very end, if you read this coordinate, this x and y coordinate, they will be the real part and imaginary parts respectively of the complex number Z1 plus Z2. Okay. So in the printed diagram, it actually shows you how to obtain the resultant vector, the vector OP3, by using the parallelogram law. What I draw separately on the right is by using the triangle law, but the effect is the same. Okay. So the parallelogram law is actually something that you have learned before in the chapter of vectors. Recall that when you add up two vectors, uh, for example, the vector u and v at the top of your screen right now, if you want to add up u and v, another way to obtain the green color resultant vector would be to place your u and v in a diverging position, such that they start from the same starting point. So if I place my u this way, I place my v this way, then if we want to apply the parallelogram law, we just need to complete a parallelogram using vectors u and v as the two sides of the parallelogram. So you can complete your parallelogram this way. And the vector that connects the starting point, the common starting point, to the opposite vertex of the parallelogram, this would be the resultant vector u plus v. And if your diagram is drawn accurately and to scale, you will notice that the green color vector that I obtained here and the green color vector that I obtained here by using parallelogram law, it will be the same vector. The two green vectors that you can see on the screen right now, they will have the same length and the same direction. Yeah, so whether you want to obtain the resultant vector by using the triangle law or the parallelogram law is up to you. The final result that you get, the resultant vector that you get will be the same, regardless of which method you use. Okay. Now, let's read through the point, the notes here. Okay. By completing the parallelogram OP1, P3, P2 in the figure above, so it's referring to this printed diagram here. Okay, so we started off with vectors OP1 and OP2, then they say you complete a parallelogram using the dotted line, and then the vector that starts from the common starting point O to the opposite vertex of the parallelogram, it will be the resultant vector of OP1 plus OP2. And so OP3, the vector OP3 would represent the complex number Z1 plus Z2. And to figure out what Z1 plus Z2 is in the form A plus BI, you just need to read the X and Y coordinate of the point P3 to be taken as a real part and imaginary part respectively of the complex number Z1 plus Z2. Okay, now let's move to point number 3. The subtraction of vector, it can also be done in a similar way. So recall that in the chapter of vectors, if this is my vector u and this is my vector v, then negative v is just a vector in the opposite direction to v, and the line remains the same. So because u minus v can be interpreted as u plus negative v, that means I can connect these two vectors end to end. Its resultant will be the resultant vector u minus v. Right, so I draw my new diagram down here. If I start with my vector u, and the ending point of vector u becomes the starting point of vector negative v, I will have such a diagram. And the vector that connects the very beginning to the very end, this would be the resultant vector u minus v. So when visualizing a complex number as vector representation on the Argand diagram, it works the same way. Right. So here it says in the figure below, let P2 prime be negative x2, negative y2. Okay, so P2 prime would be the point representation of the complex number negative z2. Okay. So in point number 3, it's actually referring to the same example as in point number 2 just now. Okay, so earlier they set z1 to be x1 plus y1i, z2 to be x2 minus plus y2i. So negative z2 would be negative x2 minus y2i. So we can read negative x2, negative y2 as the xy coordinate of the point representation of negative z2. Right? So that's how they get p2 prime as the point representation of negative z2. And then, of course, the vector that connects the origin to the point p2 prime would be the vector representation of the complex number minus z2. Okay. So here, if I move my vector OP2 prime to this position, its direction and length would remain the same. So in other words, the vector OP2 prime is the same as the vector P1, P4. OP2 prime, this vector is the same as the vector P1, P4. Because these two vectors have the same length and same direction. Then if I travel from O to P1, then at the ending point P1, it becomes the starting point of my green color vector. I travel this way. Then the resultant, which I'm coloring in pink, OP4, that resultant vector, it will be the vector representation of the complex number Z1 minus Z2. Because I know my green color vector P1, P4, it is the vector representation of the complex number minus Z2. At the beginning, we know that OP2 prime is a vector representation of minus z2. But because vectors are free, it can be moved around as long as the direction and length remain the same. So P1, P4 being equal vector as OP2 prime. So P1, P4 is also a vector representation of the complex number minus z2. So when I travel along the light blue colored path from O to P1, then from P1 to P4, the effect is to get a vector representation of z1 minus z2. right? So that pink color vector, it will be the vector representation of Z1 minus Z2. Okay, and to read the complex number Z1 minus Z2 in the form A plus BI, you just need to read uh, the XY coordinate of the point P4. Okay. Yep. So this printed diagram, they use the parallelogram approach, okay, where they place the OP1 and OP2 prime in a diverging position. They complete the parallelogram and then they just connect point O to the opposite vertex of the parallelogram. Okay, so the effect is still the same. Okay, they still obtain OP4 as the vector representation of Z1 minus Z2. Okay. Now, just to very quickly illustrate to you using a numerical example. For example, if I take Z1 to be 3 plus 4i, Z2 to be 2 plus 5i, then on my Argand diagram, remember in the Argand diagram, the x and y axis, they shouldn't be labeled as x and y, they should be labeled as imaginary part of Z and the real part of Z. The point representation of Z1, it will be 1, 2, 3, 4. Let me change the question a bit. I change to 2 plus 3i. Okay. So the point 3, 4, this is the point representation of Z1. The point 2, 3, this is a point representation of Z2. Okay, so my blue color vector is a vector representation of Z2, and my red color vector is a vector representation of Z1. Okay, so if I want to take Z1 minus Z2, if I want to take Z1 minus Z2, then I can actually figure out the result by referring to my Argand diagram that I have there. So in my blue color vector is the vector representation of Z2. It will have 2 units to the right, 2 units to the right, and 3 units up. If I want to take the negative of Z2, I will have to go 2 units to the left and 3 units down. So since I want to take Z1 minus Z2, I will start from the ending point of my red color vector. I travel 2 units to the left and 3 units down. It will end up here. It will end up here at the point 1, 1. My diagram is not very accurate, but I hope you can see the idea here. Yeah, it will be something like this. So that, okay, wait, I think I better use, I better change the number so that the diagram doesn't look so messy. Uh, Let me just try again. Z1 is 3 plus 4i, and let's say Z2 is a simple 2 plus I. IMZ and REZ. 3 plus 4i is here. Okay, the 0.34 vector representation of Z1. 2 plus I will be 2, 1. This is Z2. Okay, I have my red colored vector and my blue colored vector being the vector representation of Z1 and Z2 respectively. So if I want to find Z1 minus Z2, I will have to travel along my red color vector, and then the ending point of my red color vector, it becomes the starting point of negative Z2. But I know my negative Z2, it should travel 2 units to the left and 1 unit down, because it will be the opposite of my light blue color vector. So let me draw some grid lines here so that you can see clearly. Yeah. Right, so my negative Z2, the vector representation of negative Z2, it will be this green color vector here, where it has the same length as the blue color vector, but in the opposite direction. So this will be minus Z2. So this very ending point here, this is actually the point representation of Z1 minus Z2. And if I connect a vector from the origin to my black point, my black vector would become the vector representation of Z1 minus Z2. And if you really read the coordinate of my black point, this coordinate is 1, 3, which means Z1 minus Z2, from my diagram, it tells me is equal to 1 plus 3i. And if you really do your computation, the usual way, taking Z1 minus Z2, which is 3 plus 4i minus 2 plus I, you do get 1 plus 3i. Of course, for usual addition and subtraction, if we are not asked to draw an Argand diagram, we are not going to draw it out. But this is just for your understanding that addition and subtraction of complex number, it can be visualized using an Argand diagram. But you will need this understanding to understand the later subtopics of the chapter. Okay. Now let's move to the next page, page number 13. Okay. Modulus and argument of a complex number. This is very important, modulus and argument. So here it says, consider a complex number z equals x plus yi denoted by point capital Z on the Argand diagram and therefore represented by the vector OZ. Okay, so it's asking you to refer to this diagram on the right of your page. Okay, so it's telling you that this point Z has coordinate x, y. Okay, so the point capital Z is a point representation, while the vector OZ is a vector representation. Okay. Okay, so first of all, just be reminded that to figure out the vector representation of a complex number, you can easily obtain that vector by starting from the origin and direct the vector towards the point representation. And so OZ will be the vector representation of the complex number x plus yi. Okay. So what is meant by the modulus of Z? Modulus of Z is the length of the vector OZ. And so in the chapter of complex number, when you see the modular symbol, you should always interpret it as the length of the vector representation. Okay. So to give you one numerical example, if, for example, z is 3 plus 4i, where the point representation is the 0.34. It's a 0.34. This is a point representation. So when they ask about modulus of z, it is actually the length of the vector OZ. It's actually length of vector OZ. Now, because your OZ is the vector 3, 4, because your OZ is the vector 3, 4, written in vertical bracket form, then the length of OZ, it must be square root of 3 squared plus 4 squared. We have learned how to calculate length of a vector in the vector chapter. And from here, you can get 5. Right. So one very quick way to calculate the modulus of a complex number is this. Okay. So referring to the printed diagram on the right of your screen, okay, the length of the vector OZ can be easily obtained by using Pythagoras theorem. Here you have a right angle. The horizontal side will have x units. The vertical side will have y unit. And so by Pythagoras, you can obtain the length of OZ. Length of vector OZ is simply the square root of x squared plus y squared. And what is x and y? They are namely the real part and imaginary part of the complex number, because at the beginning they set z to be x plus yi. So you just need to take the real part, square it, take the imaginary part, square it, add up, then take the square root, you will obtain the modulus. So another quick example, and another good news about this formula is that uh, it still works even if your x and y happen to be negative. For example, if z is minus 2 minus 3i, then modulus of z, it is just square root of minus 2 squared plus minus 3 squared. It still works. It still gives you the length of the vector representation, which in this case would be square root of 13. If you really visualize the Argand diagram, uh, real part of z, imaginary part of z, minus 2, minus 3, the point is here. The point is here. And if you really find the length of your red color vector, by Pythagoras, you would get set of 13. Another example, if your, let's say, W is 2 minus I, then the modulus of W is just square root of 2 squared plus negative 1 squared, and you get a set of 5. So again, you can visualize it on the Argand diagram. A real axis, imaginary axis, and 2 is here, minus 1 is down here. If you really check the length of your red color vector, it will be set of 5. Okay. Now, recall earlier in this chapter, you have encountered before modulus of a complex number very briefly when we studied about the product of a conjugate pair Z and Z star. Okay. So when we covered this page 3 earlier in this chapter, I told you that you just accept that modulus of Z is just square root of x squared plus y squared. But by now, I hope you can understand that because the modulus of a complex number is the length of the vector representation. And the formula to calculate modulus of a complex number is just square root of x squared plus y squared. Okay. And next, let's move to argument. Okay, so when we talk about a vector, uh, we are interested to discuss about the length and also the direction. Okay, so modulus takes care of the length of the vector representation. Argument would take care of the direction. Okay. What is argument of a complex number z? Okay, so the notation is argz. Some books will write it arg bracket z. It means the same thing. Okay. So it is the angle theta made between the positive horizontal axis or the positive x direction. Positive x direction. Okay, and the vector representation OZ. So it tells you the direction of the position vector OZ, and it tells you to refer the printed diagram on the right of your page. So referring back to the printed diagram there, okay, the argument of the complex number, it is the angle made between the positive x direction with the vector representation. It's always measured from the positive x direction towards the vector. And so this angle theta here, measured from the positive horizontal direction towards the vector, it will be the argument of the complex number z. So argument is given in radians. So the default unit for argument is in radians, and we would rarely use degree here. So later when you do questions, if they ask for argument of a complex number, by default we'll give our answer in radians. It will not give degrees. Unless the question asks for degree, then only we give degree, or else default unit is in radian. Now, the argument of a complex number is not unique. For example, negative pi over 3 and 5 pi over 3 as arguments are considered to be the same. And so this is one thing you have to take note about argument. Okay. So argument it is the angle measured from the positive x direction towards the vector representation of the complex number. Okay, so if your point z is the point representation of the complex number, then your vector oz will be the vector representation. And so let's suppose that this angle here is, let's say, pi over 3. Okay. So maybe I just draw my point representation in quadrant 4. And just to match the given example here. Okay, so let's suppose that my point z is here, down here. And my red color vector pointed from O to Z, it is a vector representation. And let's suppose that the size of this angle is pi over 3. Now, the way we define positive and negative angle is the same as in the trigo chapter. When we go anti-clockwise, it is regarded as positive angle. When we go clockwise, it is negative angle. So if we measure from the green color direction towards the direction of OZ, this is going clockwise. So we say the argument of this complex number z, it will be negative pi over 3. Okay, however, the same direction can also be obtained if I measure still from the green color direction, but I go the anti-clockwise direction. And so if I go anti-clockwise by a magnitude of 5 pi over 3, I arrive at the same direction. So it is also correct to say that argument z is 5 pi over 3. It is also correct to say argument z is 5 pi over 3 because minus pi over 3 and 5 pi over 3 would point to the same direction. And not only that, in fact, I can continue to go one more cycle. I can continue to go one more cycle. That means argument of z can also be written as 5 pi over 3 plus 2 pi. And that would give me 11 pi over 3. And I can keep going on and on. Argument z, it can also be 5 pi over 3 plus 4 pi, where I go one more cycle. Then you will get a different answer. In fact, there are infinitely many correct answers for argument of a complex number. And similarly, if you keep going the negative direction, if you keep going clockwise, you can go one more cycle so that you now have your argument z to be minus pi over 3 minus 2 pi. This would also be correct. And you can also have minus pi over 3 minus 4 pi minus pi over 3 minus 6 pi and so on. And so there are infinitely many correct answers for argument z. A compact way to list all of these answers would be to write argument z as minus pi over 3 plus 2k pi, where k is an integer. Yeah, this would be a compact way. When your k takes 0, you get minus pi over 3. When your k takes 1, you will get 5 pi over 3. When your k takes 2, you will get 11 pi over 3, and so on. So this will be a compact way to write out all possible answers. Right. So in that exam, when they ask for argument of a complex number, do we need to list all answers, or do we need to write this compact way? The answer is no. We actually do not need to list all the correct answers for argument Z. And we only need to write down the principal argument. And so that brings us to the next point. Point number 3, principal argument. The principal argument of Z is the unique value of theta in the range minus pi until pi, not including minus pi. So the range minus pi until pi is called the principal range. And so by default, when they ask for argument of a complex number, we will give our answer in the principal range only. And so there can only be one answer in the principal range. And because, and so where is the principal range? It covers minus pi until pi. And so that means that if you have a point either in quadrant 1 or quadrant 2, and then the way to obtain the argument, you're going to take the positive angle, so that your angle is somewhere from 0 to pi. Remember that 180 degrees is pi, so both of these angles are less than 180, so they fall in the principal range. But if you have a point in quadrant 3 or quadrant 4, then to obtain an answer in the principal range, we are going to measure the angle in the negative direction. In the negative direction, so that the magnitude of the angle is still less than pi. Okay. And so that will ensure that the angle that you get will fall within the principal range. And so to obtain the principal range, just remember that the angle, the magnitude of the angle, magnitude of theta is less than or equal to pi. And so in other words, you are taking the so-called shortest path from the positive x direction towards the slanted direction. You will take the shortest path. If it's in quadrant 1 or 2, you travel anti-clockwise. If it's in quadrant 3 or 4, you travel clockwise. You take the shortest path to the slanted desired direction. What if the point representation of your complex number exactly falls on the x-axis, but it's on the left of 0? What if you have a point here? Let's say this point A is the point representation of some complex number. And then you can either go to the left-hand side direction by measuring pi in the positive direction, or you can also measure by pi in the negative direction. There will be two possible answers, but look at the principal range carefully. It doesn't include negative pi. It doesn't include negative pi, but it includes pi. So the principal argument of this complex number whose point representation is A, it would be just pi. So the argument of this complex number whose point representation is A, it will be just pi. We won't take minus pi. Pi will be the answer in the principal range. So if we stick to the principal range only, then every point on the Argand diagram, it will have a unique value of argument. A principal argument is unique. Unique means there is one and only one answer. But in brackets, I say here, the principal range is sometimes taken to be from 0 to 2 pi. But this is very rare to happen in our exam question. But sometimes, if you look at some other books, some questions, they do take the principal range to be between 0 to 2 pi. But by default, if the question doesn't say anything about the principal range, we are going to take minus pi to pi. So this would be the default principal range. If the question wants you to take the principal range to be from 0 to 2 pi, they will specify. If they don't specify, we'll take the default. Okay, so the note down here, it says when we are asked to find argument of a complex number, we will by default express our answer in the principal range from minus pi to pi unless the question specifies otherwise. And so that means um, if they ask for argument of some complex number, we'll only give them one answer. We are not going to list down the infinitely many answers. We'll only give them one answer in the principal range. Okay. And next, the procedure to find argument of a complex number. When attempting to find the argument of a complex number, we should first determine the quadrant the complex number z equals x plus yi lies in, find the basic angle, then adjust it according to the quadrant. And so, in other words, it is important to visualize the Argand diagram in your mind. It is not a must to draw out the Argand diagram, but you must have the visualization of the diagram in your mind. You should first figure out which quadrant the point lies in. And so that's step number one. Determine the quadrant the complex number lies in. And so where is the point representation of the complex number? Is it in quadrant 1, 2, 3, or 4? And so you have to visualize the Argand diagram in your mind at least. So not a must to draw out. It is not a must to draw out. But you should at least visualize the diagram in your mind. And step number two is to find the basic angle theta. Um, but to avoid confusion, I better just avoid using the symbol theta here. Find the basic angle using inverse tangent of modulus y over x. So this actually always works. This is this always works to give you the basic angle. Later on page 14, we'll go through several examples on how to find argument of any given complex number. Okay, so this basic angle refers to the angle made between the slanted line and the x-axis. And just like our trigo chapter. And so the basic angle that I'm talking about here is the basic angle that I usually talk about in the trigo chapter. Step number three is to adjust the value of the argument based on the guideline below. And so this guideline, it will ensure that the answer that you get is within the default principal range from negative pi to pi. And do you need to memorize this guideline, this diagram here? You actually do not need to memorize it. You only need to know that if you have a point in quadrant 1, whatever basic angle that you get, you will just take it as the argument. If you have a point in quadrant 2, if you have a point in quadrant 2, the basic angle will be here. The angle made between the x-axis and the slanted direction. So to obtain the argument, you always start measuring from the positive x direction. So you can go all the way until pi, but you have to reverse by the basic angle. So the argument here, it will be pi minus the basic angle. Yeah. So that's the guideline given. In the guideline, they are using theta to represent the basic the basic angle. Okay. Okay. If you have a point in quadrant 3, the basic angle will be here. And so to obtain the argument in the principal range, we will start measuring from the positive x direction. We will measure in the negative direction, but you have to add back by the basic angle. So you go minus pi and you plus by basic angle. So the argument here will be minus pi plus theta, or minus pi plus the basic angle. Yeah, and that's what the guideline says there. And finally, if your point is in quadrant 4, then the basic angle will be here. So you just take the negative of the basic angle. You just take the negative of the basic angle as the argument. Now let's move to page number 14. Yeah, so the note down here says when you are already familiar with the procedure, you can actually do all the three steps above at once. And so in your working, you do not need to do using three separate steps. Eh, Here I'm just telling you what are the procedure in steps, but you don't really need to perform it in three separate steps. You can do all three steps in one go. Okay, page number 14, example 1. Find modulus and argument of the following complex numbers. Okay, so what is modulus of 1 plus I? Okay, so notice that here they are not using Z to represent this complex number. And so if you just write modulus Z, people will not know what your modulus Z refers to because the question doesn't use a symbol Z. Okay, so if you like to use a symbol Z, then you should say let Z to be 1 plus I. Then when you say modulus of Z, then only people know what you are talking about. Okay, so yeah, so here modulus of Z, it will be the square root of x squared plus y squared. Okay, so the real part squared, imaginary part squared. Remember, the imaginary part is simply the coefficient of I. We do not take I. We do not put I into this formula. We only put the coefficient of I, then square it. Okay, so that gives you a square root of 2. Then the argument of Z. Okay, so it will be helpful to visualize the point representation. Okay, the point will be 1, 1 in quadrant 1. Okay, so if it's in quadrant 1, to get the argument, you just take the basic angle. Okay, and on the previous page, you were told that the basic angle is always inverse tangent of modulus y over x. Okay, and what is your x and y here? Your x is 1 and your y is also 1. So modulus of y over x is just 1 over 1. So we will just take the basic angle straight away. Okay, so it is the inverse tangent of 1 over 1, which is just pi over 4. And that's it. Okay, for special angles, like pi over 4, pi over 3, and pi over 6, and anything that is associated with pi over 3, pi over 4, or pi over 6, for example, uh, if you have a pi over 3 here, where the argument would then be 2 pi over 3, okay, you are expected to give your answers in terms of pi. Okay, so anything that is associated with special angle, pi over 3, pi over 4, or pi over 6, you are expected to give your answer in terms of pi. Yeah, so this is the answer, pi over 4 as the argument. Okay. Now let's do question B. Okay, this time I do not want to introduce a simple z, just to show you how this can be done without introducing z. So the modulus of minus 1 plus z3i can be written this way. Okay, so it is just the square root of x squared plus y squared. Okay, x is a real term, y is a coefficient of I. So here you get sort of 4, which is 2. Then the argument of minus 1 plus z3i. First, we have to visualize the Argand diagram. We have to first figure out which quadrant the point lies in. You have -1 and Z3. -1 is is on the left. Z3 is above. So you have this point. You have this point, and you know your argument must be a quadrant 2 angle. It must be a quadrant 2 angle, which means that you go all the way until pi, then you reverse by the basic angle. So the answer will be pi minus basic angle is the inverse tangent of modulus y over x. Your y is Z3, your x is -1. Okay, so here I'm using the formula basic angle is the inverse tangent of modulus y over x. Okay, where your x is -1 and your y is Z3. Yeah, of course, if you write this as inverse tangent of sec3 divided by 1, it is the same thing, right? Yeah. Right, so this is pi minus inverse tangent of sec3. The inverse tangent of sec3 would give you a special angle, which is pi over 3. So you get 2 pi over 3. Okay, that's it. Question C, minus sec3 minus I. Okay, to find the modulus minus sec3 minus I, the modulus of it is the square root of minus sec3 squared plus with minus 1 squared. That will give you a 2. Argument of minus sec3 minus I. Minus sec3 minus 1 is down here in quadrant 4. Sorry, in quadrant 3. It's in quadrant 3. So to get the principal argument, we will have to measure the angle in the negative direction here. And so the way to obtain this slanted direction is you can go all the way until minus pi, but you add back by the basic angle. So the answer will be minus pi plus by the basic angle. And so remember that when you go anti-clockwise, it is a positive angle. In this direction, which I'm coloring in the black color, it is in the anti-clockwise direction, therefore I'm adding by the basic angle. It's inverse tangent of modulus y over x, that's modulus of minus 1 divided by minus 3. That's minus pi plus inverse tangent of 1 over 3. I get special angle of pi over 6 here, that gives me minus 5 pi over 6, and that's the answer. Okay, next, move to part D. Modulus of 1 minus I, that is square root of 1 squared plus minus 1 squared, you get a square root 2. Argument of 1 minus I, 1 is here, minus 1 is here, so I have a slanted line in quadrant 4. I know this green color angle will be the basic angle, so I just need to take the negative of the basic angle itself as the argument. So it's negative of inverse tangent modulus y over x. Y is negative 1, x is 1. This is negative inverse tangent of 1, which is negative pi over 4. That's it. The Argand diagram, you don't really have to draw it out, and no marks are given for the diagram. But what's important is you know how to do the computation correctly. Okay. For question E, this is just a real number, negative 2, without any I. Okay, but always remember that negative 2 can be interpreted as negative 2 negative 2 plus 0I. And so we are still able to plot it as a point on the Argand diagram. Okay, but anyway, let's find the modulus of this complex number minus 2. Now, if I visualize the Argand diagram, where is my minus 2? It is the point minus 2 comma 0. It is actually here. It's a point minus 2 comma 0. Okay, so the modulus of minus 2 is the length of the vector representation, which I'm coloring in red. And so what is the length of this red color vector? It is just 2 units horizontal. And so the length must be 2 units. So it's 2. And what is the argument? Yeah, the argument of minus 2. Now, because this vector representation is purely horizontal, there's actually no basic angle that we can find. It is not a slanted direction. It's not a slanted vector. It's a horizontal vector. Okay, so there's no basic angle that we can find. In other words, we will have no computation to show here. And so for such questions, I will encourage you to draw out the Argand diagram. Okay, to draw the Argand diagram, because that Argand diagram actually supports your answer. Okay, the Argand diagram would now support your answer here. Okay, or else you wouldn't have any working to show here. Okay, so for cases where your vector representation of the complex number is horizontal or vertical, okay, I will encourage you to draw out the Argand diagram to support your answer here, or else you will have no computation to show. Right. So the argument will be this green color vector, okay, going the positive direction by a magnitude of pi. Okay, so we'll just take pi as the answer. Okay, recall that pi is in the principal range, so we can accept it. Okay, and done. Next is question F, 4i. Okay, so recall that 4i is the same as 0 plus 4i. Okay, so you can use the point 0, 4 on the Argand diagram, okay, to plot it out. Yeah, so this is my point 0, 4. Okay. Okay, and my vector representation will be this red color vector here. Okay. So what is the length of this 4i? I mean the length of the red color vector, length of 4i. Well, it is simply just 4 units. Okay, if you refer to the Argand diagram, it's very clear. It's just 4 units vertically up. The modulus of 4i is straight away just 4, where you don't really need to do much computation. Of course, if you interpret this 4i as 0 plus 4i and you use the usual formula, square root of x squared plus y squared, it also gives you a 4. This is also correct. So this is just alternative. Right. Then what is the argument of 4i then? Notice that there is a right angle made between the positive x direction and the red color vector. And when you measure the angle this way, it is a positive 90 degrees. But we write in radians. Our final answer is in radians, so it is a positive pi over 2. And that's it, done. Okay, whether or not you write out the unit radian is not important. If you don't write RAD, it's understood to be in radians. When a numerical value of an angle doesn't have a unit, it's assumed to be in radians. Okay. So let's move to page number 15. Some facts about argument that you need to know. Argument of 0 is undefined. Argument of 0 is argument of 0 plus 0i. Okay, so on the Argand diagram, what is the point representation of 0 plus 0i? It will be the origin itself. And so now I'm trying to draw the Argand diagram. Now this cross here, it is the point representation of the complex number 0 plus 0i. Okay. So how do we measure the argument of a complex number? We always have a vector. We always have a vector, then we measure the angle from the positive x direction towards the vector. But when the point representation is at the origin itself, there is no way for us to draw any vector from the origin to origin. In fact, it will be a zero vector. And so this zero vector, it has no fixed direction. The vector from origin to origin itself, it has no fixed direction. And because of that, there is no way for us to find the argument. Because there's no arrow that we can draw here as a vector representation. That means there's no way for us to measure the angle made between the horizontal direction to the right to the vector, because there's no vector that can be drawn here. Okay? So this is actually undefined. Argument of 0 is undefined. Now, okay. The second bullet point here says, if the complex number is real, if z is real, that means the imaginary part is 0. If z is real, that means the imaginary part is 0. Or in other words, on the Argand diagram, the y coordinate is 0. Because the imaginary part becomes the y coordinate of the point representation on the Argand diagram. Right? So if z is a real number and you were to depict it on the Argand diagram, it will be a point with a y coordinate of 0. In other words, it is a point on the x-axis. Now, of course, in the Argand diagram, we don't really call it the x-axis, we call it the real axis. It's a point on the real axis. Okay. And so it's just like question E that we had just now. This -2 is a real number. So if you depict it on the Argand diagram, it is a point on the real axis. So if you have a point on the real axis, then depending on whether the point is on the left of 0 or on the right of 0, you either get the argument being 0 or pi. Okay, so for example, if this is my Argand diagram, if I have a point on the right of 0, then this red color arrow will be my vector representation of that complex number. So when I measure the angle between my green color direction and my red color vector, the angle will be 0. So here there is a 0 angle. It's possible to measure the angle here because there is a red color arrow and my green color direction. They just happen to overlap. Right? So here the argument would be 0. Argument would be 0. If you have your point representation on the left of the real axis and this blue line becomes your vector representation, then the argument would be pi. So this tells us if your z is a real number, then the argument of z is either 0 or pi. It's either 0 or pi. If you keep your answer to the principal range, of course. Okay. If z is purely imaginary means the real part is 0. And so one example of a purely imaginary number will be something like 4i. This is a purely imaginary number. Okay, so for a purely imaginary number, because the real part is 0, that means the x coordinate is 0 on the Argand diagram. When x coordinate is 0, the point must be on the y-axis. Point on y-axis. And so in such a case, depending on whether your point is above 0 or below 0, you only have two possible principal arguments. It's either plus pi over 2 or minus pi over 2. And so this is my Argand diagram. When we have a purely imaginary number, you either have a point above 0 or below 0. So if it is above 0, then the red color vector will be the vector representation. And because of that, your argument will be pi over 2. If it is below 0, then your argument will be minus pi over 2. So there are only two possible principal arguments if your complex number is purely imaginary. So this is also an important fact that you have to know. Okay, let's move to properties of modulus and argument at the middle of page 15. Okay, these are properties that you have to memorize, and because in later computations in this chapter, you will have to apply such properties in simplifying your calculations. Okay. So it says if Z and W are two complex numbers and N is any real number, we have the following results. Okay. So the first two results is to tell you that modulus of a complex number, it can be distributed over multiplication or n division. Okay? So this is to tell you that modulus can be distributed over multiplication and division. Just to convince you that this works, I will just uh, take, for example, z to be 3 plus 2i, and take w to be, let's say, 1 minus 4i. So let's say we are asked to find. So let's say the question is, uh, find the modulus of zw. If we do not apply this property, you can also do it in a more traditional way, where you first multiply z and w. 3 plus 2i, 1 minus 4i, you multiply, you will get the real terms as these two combination. So those are 3 minus 8i squared, and this give you the imaginary terms. Those are 2i and minus 12i. And then this is 3 plus 8. This is minus 10i. That's 11 minus 10i. And then you can get modulus of zw as the square root of 11 squared plus minus 10 squared. And then you would get 121 plus 100, that's third of 2 to 1. There is a faster method, or maybe a slightly easier method, if you use the properties of argument. So the property of argument says mod of zw is the same as mod of z times mod of w. And so that means that you don't really need to do the multiplication of z with w. So since you know z is 3 plus 2i, you can first find modulus of z as surd of 3 squared plus 2 squared. That gives you a surd of 13. W is 1 minus 4i. So you have mod of w as surd of 1 squared plus minus 4 squared. Then you get surd of 17. And then by applying the properties of modulus, you know that mod of zw is just mod of z times mod of w, which is surd of 13 times surd of 17. That gives you surd of 2 to 1. Okay, so this will be an easier way to obtain the answer without really multiplying z and w. Okay. And this multiplication here is comparatively more tedious. And so you can actually avoid multiplying the complex number. If they only ask for the modulus of zw, you can actually avoid multiplying z with w. You just need to find the individual modulus of z and w, then just multiply the two modulus. Yeah, so and the same the same faster technique can be used if you have division. And so then you can avoid doing the division of complex numbers. Okay. Then okay, the third property says if you have z to the power of n, you want to find the modulus of it, it's the same as modulus z to the power n. And so this one will be very helpful in saving you a lot of time. For example, if you are told that z is, let's say, 3 plus 2i, and they want you to find modulus of z power 5. Now, if you do it the traditional way, then you would find z power 5 as 3 plus 2i to the power of 5. And you would then expand it using the binomial expansion technique, which will generate some mass here. So the expansion of 3 plus 2i power 5 will be quite messy, and later you have to simplify. And then only you can get the modulus of z power 5. So this will be very time consuming. This will be time consuming. Okay, so A better alternative will be this. A better alternative here is to just find the modulus of z, which is quite easy to find. That's just 3 squared plus 2 squared if a surd. That gives you surd of 9 plus 4, 13. And then mod of z power 5 by the third property of modulus in the table, you know it is the same as modulus z to the power of 5. Then you just take surd of 13 to the power of 5, which is comparatively much faster and easier to compute. Okay? So here you do not need to go through the pain of expanding it using binomial expansion. Okay. Then going back to the table, the fourth property, modulus of z star is the same as modulus of z. So what is z star? It is a conjugate of z. Now, this one will be easy to remember if you can visualize the Argand diagram. So, for example, if I take z to be 3 plus 2i, then my z star, it will be simply 3 minus 2i, okay, where the imaginary part has the sign reversed. Okay, now, if you visualize the Argand diagram, okay, taking the conjugate is actually reflecting the point in the x-axis. Okay, so if this is originally my point 3, 2, if this is the point representation of z, then the point representation of z star is actually just a reflection in the x-axis, where I have 3 minus 2 being here. This should be my z star. And so going from here to here, it is effectively just a reflection in the real axis. And because the x-axis is now named as the real axis. Okay. So since we are just reflecting the point, the vector representation also gets reflected. And so this red color vector is the original vector representation of z. Vector representation of z star, this blue color vector is just an exact mirror image of the red color vector when it's reflected in the real axis. But since the blue and red vectors, they are reflections of one another, of course the length will be the same. Since the red and blue, they are reflections of each other, of course the length would be the same. And because it's just a mirror image, the length of the reflection is of course the same as the original object. So yeah, so this explains why modulus of z star must be the same as modulus of z. Yeah, it just gives you one more example. If I have, for example, w is negative 2 minus 5i, and then w star is just minus 2 plus 5i. And so if I visualize it on the Argand diagram, that minus 2 minus 5 is down here. And so this is my point w. My point w star, it will be above. And this is 5 with the same x coordinate, but my y coordinate now becomes a plus 5. So again, this is just a reflection. It's just a reflection in the real axis. And because it's just a reflection, then of course the vector representation of w and w star, they are just mirror images of each other. Right? Since the red and blue vectors are just mirror images of each other, they will of course have the same length. Okay. Yeah, so this explains why, in general, z star, the length of it is the same as the length of the vector representation of z. Okay. Okay. Z star gives you modulus of z squared. This one is actually something that we have covered on page 3. They covered in page 3. Okay, so for example, if let z to be x plus yi, okay, where x and y are a real number, okay, then z star would be x minus yi. Okay, we know that z times z star, okay, it will give us x plus yi times x minus yi. On page 3, we have already learned that when we have a pair of conjugates multiplied together, it will give us just x squared plus y squared. Now, x squared plus y squared, I can put a square root to it and then a square at the outside. So it remains the same thing. Okay, because the square and the square can cancel each other. Right, then what is square root of x squared plus y squared? And recall that if z is equal to x plus yi, then modulus of z is just square root of x squared plus y squared. And that means the inside of my green color bracket is replaceable by modulus z. Okay, and that's how we get modulus z with a power 2. Right, so I hope by now you can understand the page 3 better. Okay, we covered this on page 3. Yeah, here is page 3. This is property A regarding conjugate pair. So it is just this property being stated again here on page 15. Okay. Yeah, so these are the properties of modulus that you need to know. Okay, then what about properties of argument? Okay. One very quick way to remember the properties of argument is that a lot of these properties are similar to logarithms. A lot of these properties are similar to law of logarithm. So if you can memorize the law of logarithm, you would find this, and this very easy to memorize. Okay? So these are similar to law of logarithm. And so it's telling us that argument of z times w. And so just to show you this, how similar are they? And so if you have log base a of xy, it's the same as log base a of x plus log base a of y. And here, argument of zw, it is the same as argument of z plus argument of w. Okay, so you can see how similar is this property of argument with the property of logarithm. Right, so this helps us to memorize the property of argument. Right, so similarly, if you have log base a of x over y, log can split it into a separate log. It can split a division into subtraction. So log base a of x minus log base a of y. Okay, so similarly here for argument of z over w, we have argument of z minus argument of w. Okay, so this gives you the second property in the table. Okay, and thirdly, for property of logarithm, we have log base a of x power n. We have such a property that allows us to bring n to the front as a coefficient. So we have n log base a of x. And so similarly here for argument, we have argument of z to the power of n. You can also bring the n down. It will be n times argument of z. And so again, this is a property that looks very similar to property of logarithm. Okay. Right, then the fourth and the fifth one, it will be easy to understand if you can visualize a diagram again. And let's talk about the fourth one, argument of z star. Okay. So moments ago, we have already realized that taking the star or taking the conjugate of a complex number is reflecting the point in the x-axis. Right, so if you have the point representation of z here, then z star will be just a reflection in the x-axis. It will be this way. Right, so just now we also realized that if the red color vector is a vector representation of z, and the blue color vector is a vector representation of z star, red and blue are just reflections of one another. They will have the axis of reflection as the x-axis. Now, because these two vectors are reflections of each other, then if this angle has a magnitude of theta, this angle must also have a magnitude of theta. Now, from this diagram, I know argument of z must be positive theta, because I have to measure theta in the positive direction. to reach the red color vector. Then what is argument of z star then? Argument of z star, I will have to measure the angle of theta in the negative direction. So I will take negative theta here, where theta is just the magnitude of the angle. So this shows us that, but what is theta? Theta is the same as argument z. So that's how we get argument of z star is just negative of argument z. So this tells us that if you want to remove the star from the argument operator, you just need to put a negative in front. So this is how you apply the property of argument. And so just to illustrate to you again, if I have, let's say, this point, let's make it -3 and 2. So my z here is -3 plus 2i. Okay, then what would be my argument of z if I really calculate it? That will be, I will have to go by pi, then reverse by basic angle. So it's pi minus inverse tangent of modulus y of x. So it's just 2/3. It should be modulus of 2 over -3. So I just take 2/3 straight away because I've already applied the modulus on the -3. Okay, so if I really press up my calculator, converting your calculator to radian mode, so it's pi minus inverse tangent of 2/3. Okay, I should get 2.55 to 3 SF. Okay. Then what would be z star then? Z star will be -3 minus 2i. Okay, and it will be a point down here. Okay, so to reach this purple colored direction, I will have to go by minus pi and then add by basic angle. That means my argument of z star, I will have to take minus pi plus by the basic angle inverse tangent of modulus y over x. So this is minus pi plus inverse tangent of 2/3 minus pi plus inverse tangent of 2/3. Pressing your calculator, you get negative 2.55. Okay, so from here we see that argument of z star, it will be the negative of argument z, okay, as you can see from these two answers. Okay, so this property is applicable regardless of which quadrant your z is located. It works for all quadrants. It works for all quadrants for your position of z. Okay. Yeah, then the last one, argument of minus z. So if you want to get rid of minus from the inside of the argument operator, so how can we get rid of it? You either plus by pi or minus by pi. And whether you should plus or minus is depending on which one that gives you the answer in the principal range. So between these two versions, we choose the one that gives an answer in the principal range. Now, what is the diagrammatical effect of taking negative of a complex number? Okay. For example, if I take z to be 1 plus 3i, then minus z will be -1 minus 3i. Okay, if we visualize it on the Argand diagrams, 1 plus 3i is here. Okay, so this would be your z. -1 minus 3i, it will be down here. Okay, so if we look at the vector representation, the green and blue one, But the blue can actually be obtained by a 180 degrees rotation. It can be obtained by a 180 degrees rotation about the origin. Okay, so that means the argument of the green vector, you just need to add by pi. Okay, you can get the argument of the blue vector. Okay, but you can also minus by pi. You can also minus by pi. For example, if we are already at this green color position, I can actually go this way as well. So I can also minus by pi. Right, so whether we should add or minus by pi is depending on which one it would give us an answer in the principal range. Right, so in this case, uh, using this example, my argument of z, because z is in the first quadrant, it is just inverse tangent of 3 over 1, which is inverse tangent of 3. Let me just press up my calculator. Inverse tangent of 3, I will get 1.2490. I use more decimal places here. It's just for the sake of getting a more accurate answer. Okay, so next, argument of minus z. Okay, so I have two choices. I can take argument of z plus pi or minus pi. And so should I take plus pi or minus pi? I will have to figure out which one will give me a positive answer. Sorry, an answer in the principal range. Okay. So recall that the principal range, the principal range is from minus pi until pi. Okay, this is the principal range. Okay, so knowing that my argument z is 1.24 something, if I add by pi, it will actually go beyond pi. 1.2490 plus pi, it will be greater than pi. So I don't want to take plus pi, I should take minus pi. Yeah, so it is from there that we decide. Okay, so you have 1.2490 minus pi, then you would get negative 1.8925. So this should be still within the principal range because negative pi is negative 3.14 something. Yeah, so okay, this property here, it will be easy to remember if you know that taking the negative of a complex number, the graphical effect is actually to rotate the vector about the origin by 180 degrees. Therefore, when you talk about the argument, you either plus by pi or you minus by pi. Whether you choose plus pi or minus pi is depending on which one gives you an answer in the principal range. Right, now let's do example 2 at the bottom of the page. The complex number w has modulus r and argument theta, where theta is between 0 to half pi. And so theta is an acute angle here. W star denotes the conjugate of w. State the modulus and argument of p, where p is w over w star. And so let's list down the information here first. Complex number w has modulus r argument theta. So we actually given that modulus of w is r. The argument of the complex number w is theta, and we also know that theta is between 0 to pi over 2. Okay. Find the modulus and argument of p, where p is w over w star. P is w over w star. So modulus of p, it will be modulus of w over w star. Okay, but we know modulus can be distributed over division. Okay, that is the second property of the table here. And so, yeah, we have these two properties. Remember that modulus can be distributed over multiplication and division. Okay. So we can confidently distribute. Okay, then by applying property number 4 in the table on the left, by applying this property, we know that modulus of a complex number star is the same as modulus of the complex number without the star. The star can be removed. So that means your modulus of W star is the same as just modulus of W. And since we have a number divided by itself, you end up getting just a 1. So that's the answer for modulus of P. Next is to find the argument of P. Argument of P is the argument of W over W star. But we know argument has property that is similar to logs. So we can break down the division into argument of W minus argument of W star. Then recall that earlier we learned how to deal with star inside the argument operator. So if you want to remove the star, you just need to put a negative in front. So argument of W star can now be replaced by negative argument W. Negative argument W. So we end up having 2 argument W. And what is argument W? It is theta. Argument W is given as theta by the question. And that's it. Argument of P is 2 theta. That's the final answer. Now, it's useful to notice that because theta is between 0 to pi over 2, and therefore our 2 theta must be between 0 to pi. And so if 2 theta is between 0 to pi, the 2 theta must be within the principal range, because the principal range covers minus pi to pi. Right? So that's why we can accept this as the final answer. By default, when we are asked to find an argument, we would give our answer in the principal range. So because 2 theta is some angle between 0 to pi, it is guaranteed to be in the principal range, and therefore we can accept it as the final answer here. Right. The next part of the question is more tricky. It says, given that p power 5 is real and positive, find the possible values of theta. So p power 5 is a real number. When a number is real, then it makes sense to talk about whether the number is positive or negative. So it is a positive real number. It's a positive real number. Find the possible values of theta. You'll have to make use of the information we had just now regarding the argument of p. Because to find theta, we'll have to make use of something that involves theta. So let's write this down first. I will use this information later. Argument of p is 2 theta. This is from the earlier work. Okay. Now, since p power 5 is real and positive, argument of p power 5, we can tell the argument of p power 5. Even though we do not know what p exactly is, we can tell because we know p power 5 is real and positive. Now, recall earlier, at the top of page 15, we learned that if a number is real, the principal argument must be either 0 or pi, because the point representation of a real number, it must be a point on the real axis. So let's just visualize the Argand diagram here. Real part of z, imaginary part of z. Okay. Now, because it is a positive real number, it must be a point on the positive real axis. P power 5, it must be a point on the positive real axis. It can't be on the other side. Because if it's on the other side, its x coordinate would be negative. But here we know that p power 5 is a positive real number. So its x coordinate must be positive. Okay. Right, so since p power 5 is a positive real number, it is a point on the right of 0. Its vector representation will be this blue color vector here pointed to the right. Right, so the angle made between the positive x direction and the blue color vector will be 0. It's a 0 angle. It is 0. Okay, but then here they want us to find all the possible values of theta. Now, if you just put a 0 here and you continue to solve, right, you will end up getting the argument of p power 5 by applying the property that is similar to logs. The 5 can be brought to the front. So you have 5 argument p is equal to 0. Then you have argument of p is equal to 0. Argument p is 2 theta equal to 0 and theta equals to 0. But then um, the question says your theta must be strictly between 0 to pi over 2. So you end up getting a 0, which actually cannot be accepted as the answer. So you end up getting no solution. So something must be wrong somewhere. Now, they want us to find all the possible values of theta. So to be able to generate all the possible values of theta, we actually have to consider all the correct arguments of p power 5. And recall from page 13, that says argument is not unique. Argument of a complex number is not unique. As long as the angle points to the same direction, there are infinitely many correct arguments. It is just that usually when we are asked to find an argument, by default we give the answer in the principal range. But an answer outside the principal range is actually not wrong. It's technically still correct. So here, to be able to generate all the possible values of theta, we actually need to consider all the possible correct arguments of p power 5, which means other than 0 degree, other than 0 radian, I can also take one full cycle, which is 2 pi. I can take another cycle. I can take another cycle. And so I can have 2 pi, 4 pi, 6 pi, and so on. Similarly, I can also measure the angle in the negative direction. I can also go this way. This would be minus 2 pi, minus 4 pi, and so on. Right, so now let me fix my answer here. Right, so instead of writing argument of p power 5 equal to 0, I'm going to write it as 0 plus 2k pi, where k is an integer. And so this is the compact way to write the infinitely many correct arguments. And then only later, I can generate all the possible values of theta. And then on the left, I will still do the same thing where I move the 5 to the front. So I have now 5 argument p is equal to 2k pi. And then solving for argument p, I have 2k pi divided by 5. But what is argument p? It is 2 theta. So now I have 2 theta is 2k pi over 5. Solving for theta, it is simply k pi over 5. It's simply just k pi over 5. Now, the question tells us that theta must be between 0 to pi over 2. Right? The question says so. Since theta is between 0 to pi over 2, the possible values of k are only 1 and 2. Because if you take k equals to 1, you have pi over 5. If k is 2, you have 2 pi over 5, and that's all. You cannot take k equal to 3, because 3 pi over 5 is already more than pi over 2. So we don't take 3 pi over 5. And You also do not set k to be 0, because if k is 0, you have an answer of 0, but you know 0 cannot be included as a value of theta. And then, of course, negative values of k is not in our consideration here, because theta cannot be negative, based on the restriction given by the question. And therefore, the possible values of theta are pi over 5 and 2 pi over 5. And that's all. Okay, I will end this video here on, in the next video, I'll continue with page 16.